there, science fans! In the exciting world of chemistry, we're always dealing with measurements. We measure the mass of chemicals, the volume of liquids, and the temperature of reactions. But here's the thing, no measurement is perfect. Every measurement has a limit to how precise it can be. That's where significant figures come in. They help us keep track of how precise our measurements are and prevent us from making wild claims about our results. Imagine telling the world you've discovered a new element with a mass of 10.5 grams, but your scale was only accurate to the nearest gram. That's why understanding significant figures is crucial for any budding chemist. Think of it like building a house of cards. Each card represents a significant figure, and the more cards you have, the taller and more impressive your structure can be. But if even one card is misplaced or unstable, the whole thing can come crashing down. So let's dive into the world of significant figures and learn how to build a solid foundation for our chemical calculations. In a nutshell, significant figures are the digits in a number that we are confident about. They are crucial in scientific measurements and calculations. They tell us the range within which the actual value of a measurement falls, providing a clear indication of the precision of our tools. For example, if we measure the length of a piece of string and get 15.3 centimeters, we are implying that the actual length of the string is somewhere between 15.25 and 15.35 centimeters. This range is determined by the precision of our measuring instrument. The more significant figures we have, the more precise our measurement. This means we can be more certain about the exact value. A measurement of 15.30 centimeters is more precise than a measurement of 15.3 centimeters because it tells us that the actual length is somewhere between 15.295 and 15.305 centimeters. But here's the catch. We can't just keep adding digits to a measurement and call it more precise. The precision is inherently limited by the quality of our measuring tools. And the number of significant figures is limited by the precision of our measuring instrument. High-quality tools give us more significant figures. Think of it like a game of darts. If you're using a high-quality dartboard with clearly defined sections, you can be more confident about where your darts land. This is similar to using precise measuring tools. But if you're using a worn-out dartboard with faded lines, it's harder to tell exactly where your darts hit. This is akin to using less precise instruments. Similarly, the precision of our instruments determines how many significant figures we can confidently report in our measurements. This ensures that our data is both accurate and reliable. So, significant figures are all about being honest about the limitations of our measurements and reporting our data accurately. They help us communicate the precision and reliability of our measurements effectively. Now that we know what significant figures are and why they're important, let's dive into the process of identifying them in a number. Don't worry, it's not as complicated as it sounds. With a bit of practice, you'll get the hang of it in no time. Just follow these simple rules and you'll be able to identify significant figures with ease. Rule number 1, non-zero digits. All non-zero digits, or all numbers that aren't zero, are significant. This is the most straightforward rule. For example, the number 235 has 3 significant figures, each digit contributing to the value, and the number 1.649 has 4 significant figures, making each digit crucial for precision. Rule number 2, zeros, between non-zero digits. Any zeros sandwiched between non-zero digits are significant. They hold value in the number. For instance, the number 1005 has 4 significant figures, including the 0, and the number 40.08 has 4 significant figures as well, with the 0 adding to the precision. Rule number 3, leading zeros. Any leading or beginning zeros are not, and I mean not, significant. Be careful with zeros at the beginning of a number. They can be tricky. Leading zeros that come before the first non-zero digit, or a number that is not 0, are not significant. They're just placeholders and don't add value. For example, the number 0.0025 has only 2 significant figures, the 2 and the 5. The zeros are just there to position the decimal. The 3 zeros before the 2 don't count as significant figures. Rule number 4, trailing zeros with a decimal. Trailing zeros that come after the last non-zero digit, or a number that isn't 0, are significant if there's a decimal point in the number. This indicates precision. For example, the number 5.00 has 3 significant figures, showing that the measurement is precise to the hundredths place. And the number 0.0200 has 3 significant figures as well, with the zeros indicating the level of precision. Those zeros after the decimal point tell us that the measurement was made to that level of precision, which is crucial in scientific data. Rule number 5, trailing zeros without a decimal. This one can be a bit tricky. Trailing zeros in a whole number without a decimal point are not considered significant. For example, the number 300 has only 1 significant figure. The zeros are just placeholders. However, if we add a decimal point at the end, like this 300 point, then all 3 digits become significant, indicating a precise measurement. Remember these rules and you'll be well on your way to mastering the art of significant figures. Practice makes you better, so keep at it. With these guidelines, you'll be able to handle significant figures in any scientific or mathematical context with confidence and accuracy. Alrighty, science sheepyheads, let's test our knowledge. But first, do you want to be a sheepyhead too? Subscribe so that you ace that chemistry class. Now it's time to put our knowledge of significant figures to the test. When we're multiplying or dividing numbers, the rule is simple. The answer should have the same number of significant figures as the measurement with the fewest significant figures. Let's say we're calculating the area of a rectangle that's 4.32 centimeters long and 2.1 centimeters wide. First, we multiply the length and width 4.32 centimeters times 2.1 centimeters equals 9.072 square centimeters. Now let's look at our measurements. The length, 4.32 centimeters, has 3 significant figures, and the width, 2.1 centimeters, has 2 significant figures. Since 2 is smaller than 3, our answer can only have 2 significant figures. Therefore, we need to round our answer to 9.1 square centimeters. See how that works? We're only as precise as our least precise measurement. Significant figures in calculations, addition, and subtraction. Now let's tackle addition and subtraction. The rule for these operations is a bit different from multiplication and division. When adding or subtracting numbers, our answer should have the same number of decimal places as the measurement with the fewest decimal places. Imagine we're measuring the total mass of 3 chemicals, 12.5 grams, 3.84 grams, and 0.657 grams. Adding these together gives us 17.007 grams. However, the measurement with the fewest decimal places is 12.5 grams, which has only 1 decimal place. Therefore, we must round our answer to 1 decimal place, giving us a final answer of 17.0 grams. Rounding and significant figures. Rounding numbers correctly is essential when working with significant figures. Here's a simple guide to rounding like a pro. First, identify the last significant figure. Determine the last significant figure you want to keep in your number. Next, check the next digit. Look at the digit immediately to the right of the last significant figure. Then, round up or down. If the next digit is 5 or greater, 5, 6, 7, 8, or 9, round the last significant figure up by 1. If the next digit is less than 5, 0, 1, 2, 3, or 4, leave the last significant figure as it is. For example, if we want to round 12.345 to 3 significant figures, identify the first 3 significant figures. The first 3 significant figures in 12.345 are 1, 2, and 3. Look at the next digit, the 4th significant figure, to decide whether to round up or stay the same. In this case, the 4th digit is 4. We round the next significant figure, which is 4, up by 1. Since 4 is less than 5, you do not round up. So you keep the first 3 figures as they are. The rounded number is 12.3. Remember, rounding should always be done at the end of your calculations to avoid introducing errors into your results. Scientific notation, a powerful tool. Dealing with really large or really small numbers can be a bit of a headache, especially when keeping track of significant figures. That's where scientific notation swoops in to save the day. Scientific notation is a way of expressing numbers as a product of a number between 1 and 10, the coefficient, and a power of 10. For example, the number 6.022 times 10 to the 23rd power, Avogadro's number, the exponent, 23 in this case, tells us how many places to move the decimal point. Scientific notation makes it easy to identify significant figures because all the digits in the coefficient are significant. So Avogadro's number has 4 significant figures. For example, the number 3.00 times 10 to the 8th has 3 significant figures, while the number 3 times 10 to the 8th has only 1 significant figure. Practical examples of significant figures in chemistry. Let's see how significant figures play out in some real-life chemistry scenarios. First, molar mass calculations. When calculating the molar mass of a compound, we need to consider the significant figures of the atomic masses of its constituent elements. This ensures our calculations are precise and accurate. For example, the atomic mass of carbon is 12.011 atomic mass units, and the atomic mass of hydrogen is 1.008 atomic mass units. These values are crucial for our calculations. To calculate the molar mass of methane, CH4, we add the atomic masses of 1 carbon atom and 4 hydrogen atoms. 12.011 atomic mass units plus 4 times 1.008 atomic mass units equals 16.043 atomic mass units. This step-by-step process highlights the importance of each significant figure. Since the atomic masses have 4 significant figures, our answer should also have 4 significant figures, 16.04 atomic mass units. Next, titration experiments. In a titration, we determine the concentration of a solution by reacting it with a solution of known concentration. This method is widely used in various chemical analyses. The volume of the known solution required to reach the equivalence point is crucial for our calculations. Accurate volume measurements are essential. Significant figures in our volume measurements directly impact the accuracy of our calculated concentration. Finally, spectrophotometry. This technique uses the absorption or transmission of light to measure the concentration of a substance in a solution. It's a powerful tool in analytical chemistry. The absorbance or transmittance readings we obtain from a spectrophotometer have a limited number of significant figures, which we need to account for when calculating the concentration. This ensures our results are both accurate and reliable. These are just a few examples of how significant figures are crucial for ensuring accurate and reliable results in chemistry. By paying attention to significant figures, we can achieve greater precision in our scientific endeavors. Conclusion: mastering significant figures for chemical accuracy. Congratulations, chemistry champions! You've now journeyed through the fascinating world of significant figures. Remember, these little digits play a big role in ensuring the accuracy and reliability of our measurements and calculations. By understanding the rules of significant figures, we can avoid overstating the precision of our results and make sure our data accurately reflects the limitations of our measurements. So keep practicing, and soon you'll be wielding significant figures like a true chemistry wizard. Be sure to have a nice night, and good night.